We have an electric potential problem here. This is problem 31, chapter 25. So we have these three charges located in this equilateral triangle arrangement. You can see that the side of the triangle is 3 centimeters. The magnitude, the value of the charges are indicated there, and we're looking for the electric potential at the point indicated with the dot. So looking at a picture like this, and if you're not reading carefully, you might wonder, what is the charge that they put in the middle of this triangle? Looks like there's a charge there. How much is that? Well, if you look at the statement, what we're looking for here is the electric potential. We're trying to calculate the electric potential at that point. Electric potential, it's a property of these charges that surround or that are near a particular point in space. So a charge, any object that has a charge produces an electric field, and it produces an electric potential surrounding it. So that's what I'm drawing here with these wiggly lines. So that charge produces or modifies the space surrounding it. It gives the space surrounding it some electrical properties. Each one of these charges are going to do that. And at the point in the middle of this triangle, we're trying to figure out what is the voltage there. What is the voltage produced by those charges that are nearby? Okay, so this is a similar situation, or I guess I give you an analogy here. This would be similar to asking, what is the voltage of an outlet, right? The information or the answer to the question, what is the voltage of this outlet, has nothing to do, or it does not depend on whether you connect something there or not. So the voltage at that point in that triangle has nothing to do with whether we bring a charge there or not. That point in space has a particular voltage, and that voltage is due to the presence of the charges nearby. So we're looking for the voltage at that point. The symbol for voltage that we use is capital V. And to start the calculation, we need to remind ourselves of what is the equation for the voltage produced by a point charge. These three charges can be considered point charges. They may or may not be point charges actually, but let me show you. This equation says that the voltage of a point charge is K times Q divided by R, the distance between the point in space you're looking at or measuring the voltage and the point charge. But this equation also applies for a spherical distribution of charge. So in this problem, really doesn't matter whether those charges are point charges or not. As long as we're not inside the charges, along at the point where we're looking to calculate the potential is not inside one of those charges, the equation for a point charge applies the same. A spherical distribution of charge has the charge spread on a surface or on a volume, but it's symmetrical. And if you're interested in finding the electric potential at a point R away from the center of the distribution of charge, the equation for the point charge applies, is KQ divided by R. You just keep in mind that R is the distance measured from the center of the sphere, as opposed to from the surface of the sphere. It has to be measured from the center. So again, in this problem, they're showing us some charges there. They don't specify whether they're point charges or not, but we're going to assume that they are spherical distributions of charge, and the equation for a point charge applies. All right, so we're going to use this equation, but we're going to also label the charges so we can write things in a little bit more clear. So this charge, I'm going to call it charge 1, this is charge 2, this is charge 3. So the electric potential at that point in space in the middle of the triangle is going to be the sum. These voltages can be positive or negative. We're going to, in principle, add them. Voltage produced at point 1, voltage at point 2, voltage at point 3. Again, these voltages can be positive or negative. So what is the voltage 1? That is the voltage produced by charge 1 at the center of the triangle. So the equation says K Q1 divided by R1. K is 9 times 10 to the 9. Q1 is 1 nanocoulomb, so 1 times 10 to the minus 9 coulombs. And we need R1. So is R1 the radius of charge 1? No, we just discussed this. R1 is not that radius. R1 is the distance from the center of that charge to the middle of the triangle. So how much is that distance? We have the distance between the charges given as 3 centimeters. It's an equilateral triangle. So you're going to need to do a little bit of geometry here. We're going to draw this right angle triangle formed by one of the sides will be 1.5 centimeters because that's half of the length of one side. Notice that there's a right angle triangle there, and therefore R1, the distance between charge 1 and the center, is the hypotenuse of this right angle triangle. One more thing to notice is that this is an equilateral triangle, so each internal angle is 60 degrees. We only have 30 here, so we should have, using trigonometry, we should have that R1, the hypotenuse, multiplied by the cosine of 30 degrees should be equal to 1.5 centimeters. I'm going to write it again, being careful with using MKS units, as 1.5 times 10 to the minus 2 meters. And solving for R1, we get 1.732 times 10 to the minus 2 meters. So we know that distance now, R1, we plug it in the equation. And notice that 10 to the 9 and 10 to the minus 9 in the numerator will cancel. And the answer for V1 is 5.2 times 10 to the 2 volts, or 520 volts. Alright, so that's the voltage in the middle produced only by if charge 1 was the only one nearby. But that's not the only charge. We also have charge number 2 nearby. So the voltage produced by charge 2 in the middle of the triangle would be same equation, K Q2 divided by R2. Notice that R2, the distance between charge 2 and the center, is going to be the same as R1 because this is an equilateral triangle. We're right in the middle of the triangle, so everything is symmetrical. So R2 is the same as R1, which we calculated before. The charge Q2, notice that is negative and twice as big as charge Q1. So this is going to save us some work here because the answer should be twice negative, but twice the answer for V1. That's because the charge Q2 is twice or 2 times as big as charge 1. So it should be 2 times 5.2, which is 10.4, and it should be negative because the charge is negative. So that saves us some work here. The voltage of charge 2 is minus 10.4 times 10 to the 2, or 1040 minus 1040 volts. For V3, charge number 3, what is the voltage produced by the charge number 3 in the middle of the square of the triangle here? Well, again, the charge is the same. Charge 3 is the same as charge 2, and the distance R3 should be the same as R2, same as R1. So these two answers should be the same. The voltage 3 and the voltage 2 should be the same. So we get also minus 10.4 times 10 to the 2 volts. And now putting everything together, again, the voltage in the middle is the sum of the voltages produced by each charge. So we have 520 volts minus 1040 for V2 and minus 1040 for V3. And the final answer is minus 1560. And to be consistent with significant figures, we should write it as minus 1600 volts. Alright, that is the final answer for this problem. I hope that is useful.